like that. Okay, hi, at this point, you've all met me. I'm Adam, or ACP in chat. To anyone watching this, not live, full disclosure that it is about 9:30 in the morning and that the hackathon started at 4 p.m. yesterday. So everyone's kind of tired, so it might be a bit more of an informal talk than Space Dog and Strong Game with their, very niche skills. And the HDMI connector also doesn't work very well. Okay. So, what is embedded development? It's really any code that runs on a microcontroller or on something in the physical world. There's a lot of up in the air stuff of what might count as embedded development. For example, there's stuff running on like FPGAs or field programmable gate arrays, which are actually like programmable gates of or programmable arrays of gates, like individual logic gates. That's less traditional software embedded. That's more like electrical engineering sort of stuff. There's PLCs, like programmable logic controllers. That's also more controls engineering. So at least in the case of this talk, when I'm talking about embedded development, I'm specifically talking about code that runs on a physical machine, a physical device that is probably built into some hardware or something, most likely on a microcontroller. So for examples, these are everywhere in modern society. They're in pretty much every home appliance at this point. If your home appliance has anything as complicated as a timer even before you think of Internet of Things, like if your coffee maker has an option to like brew automatically at 8 in the morning, that's probably a microcontroller doing it. Your fridge probably has a microcontroller in it somewhere with a sensor in it that's detecting if the door is open or if the temperature is right. Your television, especially modern smart ones, definitely have stuff in it all the time. They're probably not even just running like a microcontroller. They're most likely running an entire Linux kernel, which I guess kind of goes from our traditional discussion of embedded, like on something like this, to really just running a straight computer. They're super prevalent in pretty much all the industries. So anything in the healthcare industry, for example, pacemakers, heart monitors, assembly lines and such for industrial stuff. Centrifuges, I know Allie gave a talk. Did you mention Stuxnet? You said Stuxnet in your talk, right? Oh, okay, never mind. I thought Allie had a thing on Stuxnet, which is a really cool malware that attacks centrifuges, for example. Alex, did I hear you say you work at Stryker?
No.
No, okay. I thought someone said they worked at Stryker. Maybe I was mishearing it. Because I know a few kids that work at Stryker that would be doing a ton of embedded work on stuff like pacemakers.
I said one of my good buddies works there, yeah. I don't understand.
And then we have really, really important time-critical systems. Automotive systems, power plants, satellites, aerospace systems, and very complicated systems as well. These are considered real-time systems. We think of computers as in real time, but if you think about it, you might click on your web browser in Linux, and yeah, it opens immediately, but it might take a moment to load. When you're guiding a plane, that doesn't fly. No pun intended. When you're running your nuclear power plant, that 5-minute delay cannot happen. These systems have to respond usually in a measure of sub-milliseconds down to the nanosecond. And that's where even just normal embedded hardware won't work. You have to run a specific real-time, not even kernel, but a specific real-time operating system to make that happen. So a lot of the challenges of embedded development are you're running on a really tiny computer. I mean, in the case of the classic Arduino here, this is running on an Atmega 328 something. This has like, I don't know, The RAM is measured in megabytes, and I think it's less than 100 or something like that. It's not a whole lot of RAM. You're also doing low-level programming. Since you're often interfacing with individual registers and the like, you might be using assembly code. Certainly using C or C++. This is changing a little bit more as processors get more powerful. So there's stuff coming out like Microprocessors, for example, which you might not see so much in a professional setting, but you might be running Python on a microcontroller through like a translation layer for a hobby project, because it's honestly just easier than learning the memory management, which comes with like C. And the other challenge and capability, as I said previously, is full real-time systems. Again, some things do not have any flexibility. If your car airbag goes off, even nanoseconds too late, that's bad. So those have to be right on. And that makes challenges, but also modern microcontrollers are really the only things that can do that. So it's a pretty cool capability that they got too. Now, the embedded stack doesn't necessarily look like what you'd expect a normal programming stack to look like. One, you have the hardware, which is going to be some sort of microcontroller, or like I mentioned before, a PLC or a FPGA. The languages are usually low level, like C, C++, and assembly. As I mentioned, there are some other languages, like Micropython is used a lot for hobbyists. And some other systems languages are becoming more popular as well, like Rust, for example, is moving into systems development a lot, as is Go, another systems language developed by Google. I know Zig is an up-and-comer, but I have not heard of it running on microcontrollers yet, but it seems like it would be good at that sort of thing too. And then finally, the tool chain. Since you're, again, running on specific hardware, you're probably using lots of specific compilers and sometimes specific IDEs and protocols to compile the code to what might be a completely unique CPU, or at least a pretty unique architecture. So it can be a lot to even set up what you need to install and run the code on your controller. Here we have some examples of microcontrollers. All four of these I actually have right here. This is the most common one, and probably if you have ever worked with a microcontroller in school, the one you're using. It's a Arduino Uno, which is a really, really good starter board because it has a few pins there. It's got an easy power jack, like a connector, USB-B, I think, which makes getting everything set up pretty easy. And they're not that expensive. They have a lot of really good starter kits, like this here, that lets people get running fast. This one is another one, and this is a personal favorite of mine. This is an ESP32 from a company called Espressif. It's a slightly more powerful version of the ESP8266, and the amount of power that you get for what you pay for these is incredible, honestly. The thing about these boards is technically the boards themselves are not the microcontrollers. These are development boards or breakout boards, for example. The actual microcontroller, at least in this case on the Arduino, is this like centipede chip. On the ESP, the actual microcontroller is this right here. It has a shield on it, this one actually, because it has built-in Wi-Fi and Bluetooth. And what I really like about, or everything else on the board is like power supply, for example. It's the actual circuitry that the hardware needs to manage things like supplying power, charging, outputting to the different pins, and the like. Anyway, what I really like about the ESP32 is these things are just dollars. Like, you can go on Amazon and get a pack of 3 for $20. They're super cheap. And they are significantly more powerful than the Atmega. They have, I don't know how much RAM it is, but it's like 4 or 5 times more, and the processor's just much more powerful too. Which allows it to run Wi-Fi. So you can run a web server directly on this thing like you would run on a Raspberry Pi for a fraction of the cost. And you could use it to remotely control a robot or a light or whatever. And they also have Bluetooth built in, so you could control it from like an app on your phone. This is an MSP, MSP 430. If you're in assembly language, if you've taken that class yet, you will be totally used to this. You actually have to program the assembly language on this and run it directly on the board. These are, again, this is the actual microcontroller, I believe, in this case. The MSP is specifically known for having really, really good ultra-low power draw capabilities. So in super constrained power systems where there is very little battery to go around, these things can go into sleep mode and draw like nanoamps for very extended periods of time. So I know that they're often used for applications in which battery life is at an absolute premium. I know Sphinx, at least one of the examples he gave when I was taking the class, was he found an actual like charger block, like for your iPhone, that used that as the main controller. Obviously that doesn't have the same power restrictions that some things would, but it is an example of what you could use a microcontroller for. And then finally, this is the BeagleBone. This is really interesting because this is much more like a Raspberry Pi, where this is a full computer. You run Debian on this. You flash it, and there's an Ethernet port, so you can easily control it over SSH, but you also have USB ports, so you can control it that way. And if you really wanted to, you could just plug into the mini HDMI and get a straight GUI on it. But since it is a full Linux-capable machine, like a Raspberry Pi, you have the ability to write software in your standard tech stack using standard Linux tools and using that to interface with the outside world. The Raspberry Pi does this as well, but this just has way more I/O, honestly. Like, all of these pins do very complicated things, from running different buses to having plain digital I/O, or in some cases even having the capability to like wire to external memory and stuff. The other cool thing about the BeagleBone is it has what are called PRUs, I believe, which are programmable real-time units. Since the BeagleBone is running Linux, it is not considered a real-time operating system, so it would not be good for certain, tasks, again, like flight guidance software. So they actually introduced two pieces of physical hardware on it that you can interface with using C that will let you have those running on their own to give you real-time control. I was working with Wally when I was in school, and we were building a satellite, and we chose to go with the BeagleBone because it is approachable enough that students can learn to do it. We didn't have to learn an entire real-time operating system. It's incredibly powerful because the massive amount of I/O met pretty much all the requirements of our hardware needs. And having the PRUs on board meant that we could easily get that easily is a relative term. We could get access to real-time control if we ever needed it. Because a lot of times when you're doing stuff like that, you're taking into account like time dilation and stuff, because the satellite moves so fast that the clocks might be a little off if you're doing GPS work. So having really fine-grained control is super important for that sort of thing. So how does this actually work? A microcontroller is basically a system of inputs and outputs in the same way that you would think of code as inputs and outputs, instead of putting in a keyboard and getting output to a screen, or uploading a file to a web server and getting the output of that file modified or what have you. You have physical outputs, which are usually digital and electrical signals. So our inputs in this case are generally things like, here we've got a little joystick. We can put this on the top. So the joystick is essentially a potentiometer, where as you move it around, it will send signals out of the 4 pins here. Almost every sensor has some sort of, not interface, protocol that it uses. This looks like it is using just like standard digital sensors. And it will output normally a voltage or a data signal, which will be read on one of your input pins, and you'll be able to take that value in the code and output whatever you want. So for example, if I have this little robot here with 2 motors on the side, and I have my little joystick, and I say, okay, if we get this voltage in on pin 1, for example, output this voltage on pin 2, which might correspond to turning on one of the motors, which would make it turn or go forward depending on how you program it. There are all sorts of cool inputs and outputs. Obviously servos, like a motor, is a big one of the most common ones. You have LCD screens like this. There's some really cool libraries. There's an entire array of pins on the back here that are all labeled. You oftentimes have to actually read data sheets and understand what individual pins do, like what data you're writing to what. And that can get a little bit hairy sometimes. But say you have an LCD like a liquid crystal display, Arduino normally has a lot of really, really good libraries to help you get up and running with this fast so you can avoid getting in the weeds too much. So you can plug this into your little breadboard and write the status. Say you have a temperature sensor recording the temperature in your room or whatever. You can have it right in real time to this little screen because it's a cool project. Now if you look at the actual pins over here, you guys probably can't actually read the screen, can you? It's probably kind of, okay. Well, I guess a brief overview. Each of these little rectangles is a capability of a pin. So each of these pins, you can see there are 19 on this side, and I think some of these are mapped to the same. Either way, each of these little black boxes is a pin, and each box next to it is a capability of that pin. So for example, we have pin 2 here, can be digital. D2 is a digital in that, or a digital out. That just reads, is there a signal, or am I outputting a signal? It's normally has a certain voltage level. I believe that it runs on 5 volts, so it can read a 5 volt signal, or it can output a 5 volt signal. So really good for just pressing a button, for example. You might have one input on pin 2 and then one input on pin 3, and you say if pin 2 gets a voltage, also known as push a button, then pin 3 outputs a signal which might flip a transistor to turn on a light or power an LED, to make an LED blink or something. Some of the pins are a bit more complicated. Like down here, 0 and 1 have what is called TXD and RXD. That means transfer and receive for a protocol called I2C, which is stands for Inter-Integrated Circuit. It's a really cool protocol that basically you send data serially down the line to an entire, like you can have a bus full of different controllers, and you send data in bytes as opposed to just simple on and off. And only the right device on the bus will receive the data because you send it with a head. So you might have a bunch of different output devices on the bus, each that have their own hex, basically code, and it will send the data all the way down the bus, and only the stuff that needs to get it will actually read it because each chunk of data you send has a nice clean header file, or header chunk, that will say, oh, only read this if you are device OX 4A or whatever. And you can run a lot of devices on those things, for example. There are other protocols like SPI, which stands for Serial Peripheral Interface, I believe, which lets you run stuff in parallel. So you can have, maybe I'm wrong on that. There are more data in and out lines than I2C, so it's a lot faster. So it's used for things that require higher throughput oftentimes, like TFT displays to actually display stuff on like, not just an LCD screen like that, but like an actual graphics library, graphics on a screen. We also have CAN, which which would be controller area network, which is another protocol I've never used that much, but it's used a lot in automotive because it's pretty robust. And might control a whole bunch of sensors on your car and run them to a master computer or a master board somewhere, which lets it read all of it. So that's kind of like pretty heady. Obviously, that's a lot there. If you ever want to go through and look at a data sheet like this on an Arduino, the Arduino is a great way to get started. They're pretty easy and cheap. And I guess let's go over an example of an actual project. So I meant to get this working today, but Avalon kind of got in the way of that. So we have a demo, I guess, that doesn't actually work. So this is a 3D printed car that Patty actually made a while ago and printed. And we have 2 motors on the back side here, both with input cables. So these are just a positive and a negative. And specifically, we have sensors on the front. So this is a standard IR sensor that would sense like a hand dryer. You put your hand under it, it would just turn on. And this is an ultrasonic sensor. So I never got this working completely, but the IR sensor is pretty simple. It just outputs like an on or off value, while the ultrasonic sensor is a bit more complicated. It actually has 4 pins on the outside, or on the output, because it will send out a signal, bounce back, and tell you basically how long it took. So you can use that to measure how far away something is. So the goal for this was to have all of that data feeding into an Arduino and have the little robot drive just on a surface or something, and once it gets to a wall, turn around and avoid the wall, or if it drives up to an edge, since these are angled down, turn away from the edge and prevent it from driving off. Obviously, it is not actually working. There's not even any batteries in it right now. But that is an example of a project that you could do relatively easily, honestly. Starter kits like this one up here have great books that have tons of cool projects you can do with them. Here's an example. Hello. Here's an example of how you can actually get started with something easy peasy. So Arduino has a IDE. I don't like it. It's not very good. It uses their own special like sketch files, which is technically mostly C++, but it's not very transferable, and it doesn't really teach you. Well, it teaches you the basics, but it would be weird to go from that to a normal IDE at like a few students. So if you're trying to get into embedded development in the first place for fun or for work, I'd recommend trying out Platformio, which is a really awesome plugin for Visual Studio Code, because it has a whole bunch of stuff built right in. So from the get-go here, we can see that there's a setting down in the left for libraries, boards, platforms, and devices. So you can, for example, go, I want to program on the Arduino Uno, and just plug that in, and here we go. Cool, we have the Arduino Uno board that is running on the Atmel AVR platform and supports the Arduino framework. And we can just download this. We don't have to worry about all that toolchain setup. It will just do it for us. Same thing with libraries. So if we want, for example, like a liquid crystal display library for that LCD screen, here we have liquid crystal I2C, an easy way to control an LCD screen over an I2C connection, like I was talking about earlier. Say we don't want to use it on Arduino, we want to use it on the ESP32. Boom, we have a cool fork right there. We don't have to worry about compiling stuff. It just works out of the box. Knowing how to compile stuff is important, but it is a good way to scare off new programmers, because it's not very fun to deal with build issues when you could just jump into it and build cool things. So how would this actually work? It's really simple. You literally just go to new project and you get to make your project name. So we'll just say test project, for example, and select what board you want out of 1,500. So they've got everything. So they have so many frameworks. Let's say we want the expressive 32. The best part about this is it has a bunch of different frameworks, so we can run it in Arduino or the ESP IDF, which is the official expressive internet development framework, which is a fork of FreeRTOS, another one of those real-time operating systems. We use schedulers and threads. They're basically multi-threaded to allow you to very accurately schedule the times of stuff. That is a fork of that has all of the cool internet features and wireless features of the ESP built right in. This thing also has really cool, like, it's called SPIFs. I think it's called Serial Peripheral Interface File Storage System or something like that. I don't know. Which lets you store stuff after reboot on it. So you can store credentials to log into a Wi-Fi network or such, which is really awesome because if you reboot these machines, there's no technical storage on them normally. They will wipe themselves. So the fact that this has actually some onboard flash is super cool. We could try, for example, the STM32. That's another huge brand, and there are a ton of frameworks for this. We've got Arduino again, STM32 Cube. That is their official version of, I don't know what it's based on, probably FreeRTOS as well. They have an entire IDE specifically for programming that thing. Zephyr RTOS is another relatively new open source RTOS, I believe. I've never used it. And I don't even know what CMSIS is or libOpenSea. I don't know. You can try them out if you wanted to, but I have no idea what to do. So I guess we'll just go to the Arduino because it's easy. And choose the framework Arduino because it's what we've got. Just click and finish, and it will initialize right there. We won't have to worry about building or anything. I don't know if I'm going to wait for it to finish because it can take a second. But this is a super easy way to get up and running with this sort of thing. Just straight out of the box. That being said, I don't really have anything else, so if there are any questions, feel free.
I know you did some work with the MSP for your senior design. Can you tell us any more about that?
That was kind of a mess, I'm going to be honest. As all senior design projects are. So the ESP, or not the ESP, the MSP, back in my day, you had to wire these by hand. There's a bunch of like LCD, or